Hello and welcome once again for another EE324 video. Today we'll be discussing poles and zeros of the transfer function. This will be the first part of the lecture and there'll be more to come. So poles and zeros, this is going to be the first part. And what we're going to be interested in is stability. In fact, really, as we'll see in a moment, it really only matters what the poles are for what we care about in terms of stability. And I should be probably pretty more precise. When I say stability, I mean what is known as Routh's criterion for stability. Or this is for, say, input-output form. It's called Routh's criterion, and it's called Hurwitz stability for state space form. So both of these will actually tell you exactly the same thing in terms of stability. It's just one will be in terms of finding the poles of the transfer function, which is what we're going to be doing today, and the other will be by finding the eigenvalues of the state space matrix, and they both, since they're equivalent forms of the system, they will both tell you the exact same thing. Okay. And so we're going to just again focus on a single input, single output system as we have been doing before, CISO. So let's do an example where we try to find if it's stable or not. So let's look at, suppose our system is governed by an input-output equation that looks like this. It is pretty rare to have the same number of, the same order for the differential equations on either side for the input and the output, but it does happen. So why not take a look at one where it does happen? So to get this, first let's get this into the transfer function form for more practice. So recall that the transfer function, we look at the equations without accounting for initial conditions. So effectively, we set the initial conditions equal to 0 for all of the initial conditions, both for the input part and the output part. All initial conditions are set to 0. And by doing so, we can actually just doing the Laplace transform of this is really simple once you do that, because we don't have to account for the initial conditions. Right, so we took the Laplace transform of each side, and our transfer function h of s is always going to be equal to the output over the input function, but you have to be careful because this obviously seems confusing, but the coefficients of the output end up in the denominator, and the coefficients of the input end up in the numerator. So we have this. Okay, so that is our transfer function. And we're going to want to find the poles and zeros of these. And as I mentioned, the poles are going to be the important part. So these are going to be the poles. The zeros of this will be the poles. they're the poles of h of s. So effectively, that's where the transfer function blows up to infinity. And these are called the zeros. Okay. So we have the zeros of the numerator are the zeros of the transfer function, and the zeros of the denominator are the poles. And basically, Routh's criterion says if the real part of the poles is negative, the system is stable. So I want us to think about why that is, and we'll do some more thinking about that in a moment. But let's actually see what the poles are. So what I'm actually going to do is I'm going to pull up a video that I pre-recorded here, which shows how you can use MATLAB to find the poles and the zeros of this, and we're going to plot this in what's called the complex frequency plane. So basically, where S is complex, it's also called the S-plane. So the S-plane or the complex frequency plane. The first thing is I'm going to get all of the coefficients here, and the coefficients, if you look back at what I did, are the numerator and denominator that I showed there. And the zeros are the roots of the numerator. So MATLAB, we can get those roots. And the poles are the roots of the denominator. So we can get the poles. And I'm going to plot the poles here, the real part of the poles and the imaginary part, because we're plotting in the complex plane. So we typically think of the x-axis as being the real part and the y-axis as being the imaginary part when we do these plots. I forgot here to put, I'll fix that in a moment, but I forgot here to put hold on in between. So I just accidentally plotted over the poles, so I'll fix that in a moment. And then I'm going to put a line, an x line, at 0, and that's going to be the place, and it's kind of hard to see the x line at the moment, so I'm going to also change the x limits so that we can see where that is better. So changing the limits here in the plot, I'll be able to actually separate the two sides. So the left-hand part of the plane is where the real part is negative, and the right-hand, so on the left-hand side of that 0 is where the real part's negative, and on the right-hand side is where the where it is positive. And so then we can actually assess the stability by looking at if, by Routh's criterion, if all of the poles, so all of those x's, are on the left-hand side of the plane, then it's stable. And you can see that they are in this particular case. So in this case, we know that our system is stable. And what that means is that there's not going to be any growth, there's not going to be growth towards infinity, basically. It might initially grow, and that can be related to multiple things. It could be related to initial conditions. It can be related to the system itself, which might actually allow for some kind of transient growth. But in the end, everything's going to decay towards whatever the steady state is. So the steady state could be really boring, where the system just stops moving altogether, or it could be sinusoidal, right? As we've seen before. And these are related to the initial condition, or these are related to, sorry, not the initial conditions, these are related to the solutions of the system that we've seen before. These linear differential equations can have a couple of kinds of solutions depending on if the roots are imaginary or not. As you should recall, if they're not imaginary, if all the roots are real, then you're either going to get exponential growth or exponential decay, because you're going to get e to the something power. And if they're imaginary, then you'll get sinusoidal type behavior. And if they're purely imaginary, it'll be sinusoidal without any kind of decay or growth in the sinusoidal term. So then we'll be able to start thinking about things like transients. So now that I've plotted everything here, you can see the stability threshold is that x line that I did before. And we could see that all of the poles in this particular example were on the left-hand side of the equation. So that means that this system is stable. I'm going to say this one, okay? Because we were able to do that plot. So you should be able to do a plot like this. Now let's actually start talking about steady state, okay? Transient and steady state. Of stable systems. And the reason that I say stable systems is because, by the way, if any of those poles were on the right-hand plane, it doesn't matter if most of them are on the left and one is on the right, the system is unstable. So it means all of the poles have to go on the left-hand side of that region of the complex frequency plane, or the S-plane that we were looking at, okay? So if the system is unstable, even if it only has a single mode, for instance, that is unstable, then it makes no sense to talk about the transients or the steady state, because you're going to end up growing towards infinity. At least one of the modes will end up growing towards infinity, which will drag the whole system off to infinity. And obviously, you can't make it all the way to infinity in a real-world system, but something will eventually break if you have this kind of growth, right? So eventually you'll have the system break down in some way and stop working. So we really want our systems to be stable. This is an important thing. And if they are stable, then we can start talking about something that makes sense, which is the transient and the steady state. So the transient response decays towards 0. As t goes to infinity. So any kind of exponential term with t in the exponent is going to, and it has a negative sign in front of it, I should say, is going to decay towards 0, whereas the steady state response does not. Basically, no growth or decay. So you can imagine, for instance, suppose my solution looks like x of t, my solution to the differential equation, right, that we've been looking at. Suppose the solution looks something like this, say e to the minus 3t plus 2e to the minus 2t plus e to the minus t plus sine of let's say 3t plus 2 times cosine of 3t. Okay, so these are steady state terms. Why? Because they're sinusoidal. And these are the transient terms. They are going to decay towards 0, right? Or how about x of t? Let's do another example. I should call this example. Say it's e to the minus 2t times sine of t plus 4 cosine of t, something like this. This is something we could solve with initial conditions, right? So we get something like this. Then this is all transient. And the steady state is motionless. X of t equal to 0, right? Why is this transient? Well, because notice that even though we have sinusoidal terms, they're decaying, because this is multiplying this, they're decaying towards 0 anyways. So this would be like a transient response, and the steady state is with the system completely motionless at x equal to 0. We call this fixed point, a fixed point. And your fixed point doesn't have to be at 0, but because you can when you add in the inputs to the system, it may change where the fixed point goes, right? Okay. So there's an interesting thing when we are dealing with the inputs. So the inputs right now, you can think of all the stuff that we've been looking at up to this point. When we were looking at stability, for instance, first of all, we didn't care what the initial conditions were because this is a linear system. So in the end, initial conditions in that case just act as like stored energy, and if the system is going to decay towards 0, then it doesn't matter that you started with some stored energy. That just means that you start at a higher point or a lower point, but eventually you're make your way towards 0 in the long run. So initial conditions actually in a linear system don't play a role here, other than changing the initial state. Okay, so the initial stored energy. But what happens if you have an input? Well, recall again, since we're dealing in these are linear equations that we're dealing with, the input always is a term that we would call the non-homogeneous part of the equation, right? Because that's where the u goes, is on that, the system, it's whatever the differential equation is, equal to u, or u dot or whatnot terms. So because of that, we may think about particular inputs, and many of the most common have the following form. So many of the most common inputs have the following form. U of s is equal to n of s over d of s, where n and d are polynomials of s. For instance, let's say the Laplace transform of 1 Laplace transform of 1 is equal to 1 over s, which is a polynomial. And so 1 is a polynomial. It can be thought of as a polynomial. And s can be thought of as a polynomial, right? The coefficients of the top polynomial are just 1, and the coefficient of the bottom polynomial is 1 and 0, right? Because you could have had an s plus something, and so the coefficients there are 0, but 1 and 0. So these are two different polynomials. So many of these can be thought of as a polynomial divided by another polynomial. I encourage you to go look at the common Laplace transforms of a variety of functions, and you'll see that many of them look like this. Note that if you have something that looks like e to the something times something like this, that is not a polynomial. E is not an exponential function is not a polynomial. So in this case, that assumption wouldn't work. So in the following, we'll assume this exact form, u of s equal to n of s divided by d of s. But we will keep in mind that this is not always true. Okay? And when we do this, then we can actually use this to our advantage to examine what what would happen with a particular set of inputs. So as an example, our transfer function, which was equal to s cubed plus s squared plus 3s plus 2 of our original example here, s cubed plus 2s squared plus s plus 1/2. That's our transfer function. Then x of s, let u of t input be equal to minus 3 times the sine of 2t. Then we know that u of s, after taking this is the Laplace transform of this, is equal to minus 3 times 2 over s squared plus 4. And you can get that off of the Laplace transform table, which is the same thing as minus 6 over s squared plus 4. And we can recognize that we can find the solution of this. X of s is just equal to the transfer function times u of s. So again, we're assuming 0 initial conditions, and for linear differential equations, linear time invariant differential equations, this doesn't matter. The initial conditions don't play anything in terms of the asymptotic meaning as we go off towards t equal to infinity, as t goes to infinity, the asymptotics don't care about the initial stored energy in the system. And so, but it will be important to know the inputs, because like a sinusoidal input should eventually lead to some kind of sinusoidal, because as long as the input's not decaying, which it's not in this case, right, should eventually lead to the response being kind of sinusoidal as time goes on. Which means that we can rewrite this as s cubed plus s squared plus 3s plus 2 divided by s cubed plus 2s squared plus s plus 1/2 times u of s, which is minus 6, divided by s squared plus 4. So the nice thing is that the root, if we already know what the roots of this are, and we actually did solve for them earlier in the video, then we only get a new set of roots that are related to this, because obviously it's just multiplying times this. And we already know that this is actually sinusoidal, so this is going to be something like s plus 2i s squared plus 4 is equal to s plus 2i times s minus 2i, right? So we already know that in the end we should get some kind of sinusoidal response because of this function, regardless of what happens over here. And actually over here we actually get imaginary roots as well. So we actually get something that looks like minus 6s cubed plus, minus I needed the 6 here. Minus 6s cubed minus 6s squared minus 18s minus 12 divided by, well, I'm gonna write out a not exact thing, but the roots, the poles that we found earlier in MATLAB were the following. This is going to actually be s minus, but it's negative, so s plus 1.5652. That's not the exact answer, that's just a rounded one. Then we're going to get s plus 0.2174 minus 0.5217i and we're going to get s plus 0.2174 minus 0.5217i, and then it's also going to be times this s plus 2i times s minus 2i. And why this is actually useful now, so notice that even though we had some poles here, now we could actually think about the poles of the entire system, which is the full solution, including the inputs. So times, I should write a times here, just so that we recall. But if we look at these terms immediately, you should be able to peel apart, well, we have an exponential. If I were to take the, I'm not going to solve out the whole thing using partial fraction decomposition, but you can. Residue in MATLAB. I showed that in a prior video. So that we could solve this. I'm not going to bother with that because that's not what I'm curious about at the moment. I really am curious about these terms and what they tell me. So since we have complex poles, notice that this means it's going to look something like this. Solutions will look like A over S plus 1.5652 plus b over s plus 0.2174 minus 0.5217i. And notice that this term will look like in the inverse Laplace transform, we'll have something like this. Will look like e to the minus 1.5652t. This will look like plus e to the minus 0.2174t times something like b I'll just call it C1 sine of 0.5217t plus C2 times cosine of 0.5217t. But notice that this is a transient term. This is a transient term. But this will give me plus something like C. Actually, it's not going to be that. It's going to be e to the 0t times C3 sine of 2t, right? Because if I go back up here, this was 2i. So sine of 2t plus C4 times cosine of 2t. But this is going to be e to the 0t is going to be equal to 1. So this is a steady state term. So notice that originally in this function we had only transient terms. We had only transient terms that were going to 0. These were the contribution of those transient term of the first three terms. This one, these three, and the only reason that this has a non-zero steady state is because of the input function that we chose. So we chose an input function that looked like sine of 2t here, right? We chose this input function, and that that was what gave us the steady state solution here. Okay, so we can actually pull apart just by having the poles, knowing each of all of the poles. We can actually pull apart what's going to happen in this linear time invariant system. That's all that I have for this video. Hope to see you again soon.